Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 16, 2026, about 5 days ago. It identifies a critical flaw, where noisy retrieved contexts make large language models dangerously overconfident, and proposes a new framework that improves calibration scores by about 11%. The paper is titled, NAACL Noise-Aware Verbal Confidence Calibration for Large Language Models in Retrieval Augmented Generation Systems. And, as we'll see later, the method achieves these gains efficiently without relying on stronger teacher models. For those interested in the implementation, the authors have shared their code on GitHub. Figure 1 illustrates the core problem with a concrete example. At the top, the system retrieves messy passages containing contradictory information about sports channels. In the blue box, a standard model is misled by this noise, answering incorrectly with 100% confidence. In contrast, the green box shows the new approach, where the model explicitly judges the passages, spots the contradiction, and correctly drops its confidence to 30%. The bar chart at the bottom right confirms this systematic improvement, showing a sharp drop in expected calibration error across different models. So while Figure 1 sketched the problem conceptually, Table 1 now quantifies its scale across 4 major benchmarks. The columns track performance on Strategy QA, Hot Pot QA, Natural Questions, and Bamboogle. If you focus on the average section on the far right, the numbers tell a worrying story. The expected calibration error, or ECE, consistently exceeds 0.4. Since ECE measures the gap between a model's confidence and its actual accuracy, these high values confirm that standard models are dangerously overconfident when processing noisy retrieval results. Well, Table 1 showed the broad issue, but Figure 2 dissects exactly which type of noise causes the damage. The charts track 2 models, separating irrelevant noise marked as IRR from counterfactual noise marked as CF. If you look at the expected calibration error plots on the left, notice the massive spike for the gold plus CF bars. For the llama model in the top row, the error jumps from about 0.14 to nearly 0.5 when contradictory information is added. Yet, looking at the average confidence plots on the far right, the bars remain stubbornly high, near 100%. This proves the model is just as confident when it is wrong as when it is right. Alright, having identified the noise problem, Figure 3 outlines the solution, the NAACL data pipeline. The process starts on the left, transforming raw questions into high-quality training data through 3 key stages. First, in the top right panel, the system constructs 3 specific scenarios for each question, a counterfactual group, a consistent group, and an irrelevant group. This ensures the model learns to handle the exact noise types, Figure 2 highlighted. Next, the middle panel shows the response generation phase. Here the model uses best event sampling, generating multiple attempts to find the optimal reasoning trace guided by rules like conflict independence. Finally, the bottom panel details the quality control, where strict filters, such as rule adherence and confidence alignment, refine the data down to the best examples for fine-tuning. Okay, now that we have seen how the training data is built, Table 2 presents the final payoff. This table compares the proposed framework against 5 baselines across 4 different language models. If we focus on the Llama 3.1 section at the top and look specifically at the average column on the far right, the numbers tell a clear story. The standard vanilla model suffers from a high calibration error of 0.41. But with NAACL, this error drops sharply to 0.27, while the AUROC score jumps from 0.60 to 0.75, confirming the model is effectively learning to distinguish reliable evidence from noise. So Table 2 gave us the numbers, but Figure 4 visualizes the actual calibration improvement on Hot Pot QA. The goal here is for the blue bars, which show model performance, to track the diagonal dashed line representing perfect calibration. In the top row, the chain of thought baselines are erratic, with bars often straying far from the ideal line. But in the bottom row, the fine-tuned models tell a different story. The bars align closely with the diagonal across the entire range, proving that the system now accurately assesses its own likelihood of being right. Wrapping up, 2 takeaways stand out. Retrieval noise makes large language models dangerously confident when wrong, but targeted fine-tuning efficiently fixes this. By teaching systems to explicitly evaluate their sources, we get models that are honest about their uncertainty, which is vital for high-stakes deployment. That's it for this episode of the AI Research Roundup. I'm Alex, thanks for listening.